This is the sixth installment of Advanced J1939. The last time we talked about the receive component of the CAN transceiver. Today, what I've done is I've added another controller to the CAN bus. This is a simplified controller. I've just put the switches in instead of using the FETs to control the high and the low side. What I'm going to show in this version, let's say that this is the string of zeros and ones, the beginning of the message, which this controller wants to put out onto the CAN bus. It wants to transmit this. One thing I do want to mention, I start the time of this at 2 microseconds, not at 0. Basically it gives us from 0 to 2 microseconds. We can see that the bus is idle because it would have been sitting at that recessive state for a period of time. So I'm going to start my transmission or my transmitting my message on my time when I show it at 2 microseconds. So on the second controller, let's say that we have it also has a CAN message it wants to put out on the CAN bus, and this message starts also with a 0 and a 1, but after the first 0 and 1, it wants to put this message on, so it's all zeros. So it's a dominant bit, a recessive bit, and then the rest of the bits in this 8-bit message are dominant bits. So as I indicated, the CAN bus is in parallel with both controllers. We can see here that we do know one of the rules of parallel circuits are the voltage has to be the same anywhere in a parallel circuit. So we can imagine the terminating resistors are sitting out there in parallel. All the other controllers, everything is sitting in parallel on this CAN bus. So what that means is I can't put a value of 2.5 volts and 3.5 volts, for example, on CAN 5, on CAN high. It can't be that voltage on the CAN bus. It has to be one or the other. And we're going to see how this works once we try running this. So I'll run a time domain simulation of this. I'm going to stop the time domain simulation once I hit like 10 microseconds. So that's going to be a couple of bits into the message. We'll take a look at it here. And we can see here's our idle state. The bus is sitting idle from 0 to 2 microseconds. At 2 microseconds, both controllers at the same time both transmit a dominant bit. So they're transmitting a logic 0 onto the CAN bus. And since they're both trying to take the CAN bus to difference in voltage of 2 volts approximately, so driving CAN high to 3.5, CAN low to 1.5, that's permissible. And then exactly 2 microseconds later, at 4 microseconds, both controllers want to transmit a logic 1, so they want a recessive bit. And this is allowable. Both of them are in parallel. We can do this. So we come and we get our first, in this message string, we get our first recessive bit, the logic 1. Then at 2 microseconds later, 500K CAN bus at 6 microseconds on the time since the simulation started, both controllers are also driving the CAN bus to where it is a dominant bit. So that's permitted as well, right? Both of them exactly at the same time started transmitting this message, or very close to the same time. However, we can see at 8 microseconds, the controller that we have on the left wants to transmit a logic 0, or logic 1 wants to take the bus back to a recessive state. However, the controller on the right wants to transmit a dominant bit. Therefore, the CAN bus, even though this controller on the left is trying to take the CAN bus to a difference in voltage of 0, the controller on the right is taking the CAN bus to a difference of about 2 volts. So it's transmitting this dominant bit. What that means is my device on the left has to stop transmitting. It's going to sample this. It's going to see, I expect the CAN bus to be in the recessive state. I expect a logic 1, and what it actually reads on the receive. So the orange is what our controller on the left wants to transmit. The blue is what the controller on the right is actually driving that CAN bus to. This is what it reads back. So taking a look at the logic here. So we sent out the first 2 bits, the first 3 bits were fine. Both controllers are driving the CAN bus to the exact same voltage. So that's possible, that's permittable. However, we reach this 0, 1, 2, or excuse me, 1, 2, 3, 4th bit in, and it is a logic 1 of what I want to transmit. But what I'm receiving, what I'm seeing is actually this on the CAN bus. So I'm seeing a 0, 1, 0, 0. This is a discrepancy. This would be it's not possible. As I said, I can't make the CAN bus be both a logic 0 and a logic 1. The logic 0 wins in this case. So this is arbitration, or the beginning of arbitration. So two devices have taken the CAN bus at exactly the same instant in time, which is permitted. The bus has been recessive. It's been idle for long enough a period of time that they can use the CAN bus. It may be microseconds, but it's long enough that they can say no one's using the CAN bus. I'll start driving my message, and as soon as I try to take the bus to a state which is recessive, but I read that it's dominant, I stop sending this message. That message is done. I'm not going to send it now. I have to wait. So if we take a look at the time domain simulation again, both controllers, this is the idle time. This is the time that both controllers are taking the bus to a dominant state, to a recessive state. Both take it to a dominant state. And then here's where they disagree. The controller on the right is driving the CAN bus to a dominant state. The controller on the left is letting the bus go back to a recessive state. So recessive is you're not driving anything. You're just it's the neutral, the natural state of the bus. So you're letting it go back. The controller on the left lets the bus go back to this logic 1 state, or this recessive state. The controller on the right is driving, turning the transistors on. Therefore, the actual voltage that we measure on the bus is this. We see a difference of 2 volts. So the 3.5 and 1.5. That's what's actually on the bus, even though what's expected by the controller on the left is that we would have recessive state. We would have both CAN high and CAN low be at approximately 2.5 volts. So therefore, even though it's trying to let this bit be transmitted, it's not driving it not driving the CAN bus to this dominant state. It's letting the CAN bus go back to the recessive state. The controller on the left has to give up and say, I'm going to try this message again when the bus is free. So this is the beginning of arbitration. As I indicated on CAN, there's rules, all of the controllers which are running the software, so the microcontroller on the device has to be programmed to know that if I'm trying to see in this case, a logic 1, which is a recessive state, but I read a dominant state, I need to stop. I need to stop trying to transmit because I can cause problems on the bus. I have to now let this controller have its say. It's going to send out the rest of its message, all of the information, and we'll talk at some point what all those fields are, the length of the CAN message on on J1939 in particular, what the length of the messages are. So we have to let that complete message finish, then we can get back on the CAN bus. This is one of these concepts that's a little confusing because we keep going back and forth between zeros and ones and dominant and recessive. The easy rule to remember with CAN is the lower the number, the higher the priority. So this goes back as you start looking even at controllers themselves. Each controller is given on a machine, for example. Each controller that is there is designated by SAE J1939 to have a source address, so an address, the number as to what the controller is. Myself being a former engine guy, I always like to say this: the engine controller is the most important controller on the machine. That could probably be disputed, but most machines require an engine. So the engine controller has been designated, the primary engine controller, by J1939 SAE as being a source address of 0. No one gets lower than 0. So some engine messages, if the priorities of everything else are identical, the engine will win. And we'll talk about those things as we go through more of the thing of messages. So this is part of this collision avoidance strategy, this arbitration. It's decided on early, or it's decided on by SAE. Is the most important controller, what messages are the most important, all of these things. So this is agreed upon within the industry, and so this allows you to be able to, in some cases, take some device, put it on the CAN bus that originally didn't come with the machine, and it worked fine. So kind of plug and play, if you can imagine that. So this is the beginning of arbitration. It's one of the more important concepts with CAN. CAN wouldn't be possible without arbitration.